Hello. So I showed this to my friend. This is a nope. This is an 8-bit by 8-bit multiplier I built in a game called Minecraft. And so I guess I should start. If you don't know what Minecraft is, it's like a block building game, but it does have logic components. And so I'm going to demonstrate that quickly. So you have lines of wires that can be turned on, logic 1, logic 0 off, and you can use these torches getting fed into them as inverters, and then using certain combinations of these you can get logic gates out of them, which is super cool. So for example, this would be, if we have it then go into another block, this would be an AND gate. So this would only be on when they're both on. So this is just proof of concept to show you guys that you can't actually use this to make logic gates. And so I created the multiplier, like I said, and these blue elements are D flip-flop rising edge triggered bit storage. So here is a clock signal. I guess I should show it in action first. So there's our output, here's our input. It is in the form of bits. So we'll do 1, 2 multiplied by, so it'll be 3 times 128. And then if we hit the run button, eventually it's got a little bit of delay, but eventually these will all turn off. And then I'm going to get a calculator while it calculates so I can see what the value should be. So 128 times 3 is 384. So if we go over to here, we should see this one light up. I'll just mark it so before it finishes. And then we got one. Oh, so it's actually just those two. So that's super awesome. Because 256 plus 128 is equal to 384. And 384 divided by 128 is 3. Yeah, so once it's done calculating, we'll see that it outputs that value. And this is just a big 16-bit long output, which is super neat. As I said, it takes a while to run through those clock cycles, which is over there. But on the cool, by how the design is similar to what we did in lab, it'll take the same amount of time for every multiplication. And there we go. Now I see that it lights up. It's got the correct output, which is super cool. So as I was saying, we've got 8 input bits for each of them. And so the bottom row, there's nothing fancy about it. It just takes an input. So first of all, like when you activate the system, it clock resets everything. So everything's zeros, and then it inputs the values. So the bottom row is stagnant. And then what's cool about how the top row works is it also takes in the input value, but these purple lines shift it down the line. So, and then it uses this output. So when the least significant bit is a 1, it will output the bottom. So this is the multiplicand, this is the multiplier. You get the idea, and I'll show a demonstration of how that works real quick because it's fun to watch. So we got the top row. So I'm gonna have it be just like this, and then we'll have that. Don't really care about what the output is, but I want to show you that it does actually alternate. And so right here, first it resets. So now if you look right here, this represents a logic 1, logic 0, logic 1, 0, 0, 1. So it's the right wire. And so we'll see as it progresses that whatever this is here, it gets transferred over to there. So now that's on, off, off, on, and so we should see those shift again in just a moment. And it did, on, now it's off, off, off. So that's cool. So and then whenever a on signal does reach it, so it's about to, it goes down here, and this effectively is an AND gate. And so now it's on, it's outputting the exact lever input we had for the bottom. And now, so looking at this side of the circuit, these are all full adders, and it only has inputs from here, itself, and then if it has a sum, so like let's say you input 2 bits, then it carries on over into the carry in for the next bit, and it goes up this sequence. So with that design, there can be situations where you have two ones on the final bit, so we have to have an overcarry 17th bit. And how this works is there's two lines. The orange line is adder mode, and then the green line is the shifter mode. So as we add all the bits in order, we start with the least significant and add with the most significant. So when we add our first significant or the least significant bit to our line, it should shift all the way to the least significant position, and that's exactly what will happen. So this far side represents the highest bit value, and it goes down, up, and around like this. And then once it does 8 clock shifts exactly, it'll output the correct answer. And then here, it's a really rudimentary clock, but these basically act as delays. So each of these has a 4-tick delay. So I'll hit the system so you can see how the clock signal works. But basically, that's just a timing circuit, and it connects to all the clocks of all the gates and the shifters. And so as you see, you can see the signal travels, and then when it gets to this side, it'll output clock signals to all the components, which is super important. And you can see that these two alternate because you can only have one or you can only have one or two of them in the mode. This one doesn't need a shifter here, but sorry, I stuttered. So it's either in shifter or adder mode. This one didn't have its block, and I remember it's because it shifts all the way from right here. So, and yeah, so it's still going. So it is a bit of a long delay. I probably could have shortened it, but what's super cool is that it means regardless of how big the number is, it'll always output the same, or output in the same amount of time. And then these top wires just bring the output of all those D gates all over to here, so we can view the results. Trying to think if I didn't hit anything else in terms of showing it off. Oh, I guess we can watch the output bits sequence through, because that'd be cool. So we'll do that quick. I'll fly over here. So yeah, they'll reset to the 0 value, and then it'll add for the first time. I'm not really sure what we're watching for, because I forgot what bits we had it set to. Okay, so now you see some of them light up. This bit right here just sequence shifted over here. And then it'll sequence shift to here. It did that, and so on and so forth. And eventually, depending on what stage it was added in, it'll stop. And you don't have to have adders on the top row because of how I set it up, which is sweet. Yeah, so pretty cool working calculator in a video game using stuff I learned in EE. Don't have anything else to really say about it. It has a lot of safety, so this isn't related to engineering now, but like you can't spam the input because I designed that. Same with these levers. If you change the levers while it's calculating, it won't affect the output. That's the point of the D gates on the bottom. And since I did design these all by myself, they're a little bigger. I'm sure there's like smarter designs. I'll show, yeah, so over here is the full adder. So if you input 1 bit, you can see it has an output of 1. Doesn't matter which one it is. It's always, you can see it right there. And then if we have the carry and just be the 1. And then anytime there's 2 bits, you can see that, whatever the word for it. That's the one where it goes to the next bit. So the full adder circuit here works, and then this is the NAND, not the NAND. This is the rising edge triggered D gate. And so since we had it on, it changed, and then it doesn't matter if we turn this off right now, that's still stored as a positive. And even if we have a down, so it only updates, still hasn't updated, and then when we finally clock it with a positive, then it updates to the 0, which is cool. And this is just a bunch of NAND gates wired up in a specific way. So you can see here, for example, this one connects to both of these, and then this connects to that, and then through this block it's powering it. Yeah, it's a video game. I don't expect you to understand how it works in the video game, but it's all blocks that I've placed and made like hardware components, and I was able to make a multiplier with it. Yeah, so cool. I hope you guys enjoy this video. Just wanted to display it for you. It's kind of a cool concept done in Minecraft. Cheers.